would I be thinking, man, I should have made it harder? Or would I be thinking, yes? I'll probably flip back and forth between the two.
Go with multiple choice maybe.
Ugh. As a student, I would hate having a multiple choice test. All right, let's see, so you've got master set 29 due on Thursday, and test a week from Thursday on April 1st. I do want to throw into this is that the day before the test, I'm getting my second shot. Now, some people have reacted to the second shot by their bodies going, oh, wait a second, let's produce all sorts of symptoms that you're gonna be, I've had some people who've been laid up in bed for 2 days after the second shot and things like that. They're not contagious. I've been assured that these people are not contagious. It's just their body's reaction to what they think is a contagion. So I still plan to be here. I might be looking sick, or I might be feeling fine, I don't know. But just give you a heads up.
It'd probably take it a couple days to kick in.
And then I'll grade your test, and that will make me feel better. So if I don't feel better while grading your tests, then I'm going to pick one of you and take it out on me. I'll take it out on my daughter. I'll go back and grade some of her stuff. All right, so any questions before we start talking about magnetism?
What chapter are we on? 30?
30. All right. We were just about to get to the math portion of magnetism, and so let's just start out with the math portion of magnetism. It is not a nice, simple little formula that we had starting out with electricity, or at least with charges, where we had a nice Coulomb's law. This is known as the Biosavar Law. It is not, I think they're French. It's spelled like Biosavar if you anglicize it or Americanize it, but it is pronounced Biosavar, rhymes with Leo Bazaar. So we have this use of knot right here. This is known as the permeability of free space. If we drop the little subscript right there, then it would just be the permeability of whatever the medium is. It is the magnetic analog to the permittivity. When we were dealing with epsilon and how a dielectric reacts to an electric field, we get permittivity. Now we have how a medium reacts to a magnetic field. It has an exact value, use of knot does. It is 4 pi times 10 to the negative 7 Tesla meters per ampere. We double check those units because it always seems to flow, and then I get to a certain point where I'm going, wait a second, I get something backwards. Yep, that's right. Which I think comes out to 1.28 something times 10 to the negative 6. Anyway, 4 pi times 10 to the negative 7. It's basically, when we're in SI units, this opening bit right here just multiplies everything times 10 to the negative 7 because the 4 pi goes away. This Q right here is a charge. V is the velocity of the charge. R is the distance from charge to point in space. Because you're trying to find the magnetic field at some point in space, so R is the distance from the charge to that, and this R hat is the unit vector from the charge to that point in space. So unit vector from charge to point in space. But you might be looking at that equation and go, yeah, fine, yeah, we can do that in our sleep. But there are actually 4 different variations of this. So let's start. So first off, questions on this, what I've written down, or reading my handwriting, whatever it happens to be. And then we'll talk about the 3 other variations of the exact same formula. If I have some vector here, it has a magnitude and a direction. Hopefully it's not a shock. The magnitude is r, and the direction is just some unit vector in whatever direction that vector is going in. You can do that for anything. So if there's some vector a, well, that's just equal to a times some unit vector a. In other words, I can take any vector, say we have some vector z, divide by its magnitude, and in essence, I create a unit vector. So if I have 3i hat plus 4j hat, well, if I divide by the magnitude of 5, I get 0.6i hat plus 0.8j hat, and that has a magnitude of 1, that is a unit vector. So given that, I have this r hat right here. R hat is just some vector r divided by the magnitude. So this equation right here can also be written as dv is mu naught over 4 pi times dq v cross r vector over r cubed. And personally, this is my preference of the different forms. I like the r vector over r cubed as opposed to r hat over r squared. But in essence, this bit right here is the same as this bit right here. So the second form of the exact same thing. Note that implied in this equation is that in order for there to be a magnetic field, I must have a charge with a velocity. In other words, a charge must move. And that's in essence how you create magnetic fields, is by having a moving charge. However, if I have a moving charge, what else do I have?
Force.
Is it a force?
Yeah.
Not necessarily.
Change in electric field.
Current.
I would have that. I was going more for the current. So there's a variation of this that doesn't have it in terms of this differential of charge, but has it in terms of current. So let's take a look at that. I know that dq dt is equal to I. So dq is equal to I dt. Quick glance, make sure I go into the right place, all right. I know that velocity is ds dt or dx dt or d whatever letter you're using for position dt. Therefore, vdt is equal to ds. And we just make those substitutions. I'm going to start with the top one over there. So we have dB is mu naught over 4 pi times, instead of dq, I have I dt. And instead of v, I've got ds dt. Oh, I guess I didn't need to do it that way. ds dt cross r hat over r squared. The dt's cancel out. So we get mu naught over 4 pi times I ds cross r hat over r squared. where ds is a vector in the direction that the current is flowing. Officially, current is not a vector quantity, and so we can't, it'd be really nice just to put, like di cross r hat, but this is not a vector, so we have to express the vector in terms of the direction the current is flowing. And then, similar to what we did over there, that would also be equal to mu naught over 4 pi I ds cross r vector over r cubed. And again, I prefer the r vector over r cubed, and hopefully some of that explanation for why I prefer that will come out when we do our first derivation. But I do want to point out that the Biosavar is actually our second physics equation of the course. Coulomb's law being the first one. Everything after that, everything up to the first two tests, it's just Coulomb's law, math and definitions. And as a matter of fact, that might be it. We got the two physics equations. I think we're done for the physics equations for the entire course. The rest is just making it look pretty and making it fit situations. Any questions before I read your minds? All right? That's great, but what's the magnetic field coming from a current in a straight line? Did I get that right? Is that what you're thinking?
Definitely.
All right, let's actually use this, do some calculus. Let's just start scratch. I have some current flowing in this particular direction. And I'm going to figure out what is the magnetic field at this spot right here. I'm going to call this point P, for lack of imagination. I'm going to label this distance here capital R. What is magnetic field at P? And I've got cough drops in the other room that I think Casimir is struggling.
Yeah, I was just about to leave. I got something in my throat, so
Okay.
I wasn't getting cough.
Okay. I'm not trying to chase you away. Just
Yeah.
years ago, I was at a concert downtown Richmond, and there was some kid behind me who was just coughing his lungs up. And so I had cough drops in my pocket, so I turned around and offered them one, and they apologized. And I was thinking, no, I've been there. Trying to be nice. Now you're guilting me. Anyway. All right, so in order to do this, remember we've got this differential in the formula, and I was about to point to a non-existent formula there, so let's write it up again. So mu naught over 4 pi times the current ds cross r over r cubed. So we have this differential ds, so we need to create it. So I'm going to take some little segment right here, and I'm going to call that ds. Again, it is in the direction of the current flow. R is a vector from my differential. Yes, the distance is r, and the vector is r hat. I'm going to set up a coordinate system here, and let's just make that 0 and I hat, j hat. This distance here is x, and I've already established that distance there as r, capital R. All right, Now, since this is my x-axis, and I have ds labeled, I probably should come up with some common language here. This is x, and so this ds here is going to be, well, it's dx, except it's pointing to the left, so this would be negative dx I hat. Dx, just because it's a tiny little piece on the x-axis, and negative I hat says it's going off to the left, because I said to the right was positive. Oops. I can either change that or this. Let's go back to the brainwash. I hat's to the right, J hat's up. I did have it labeled wrong. I don't know if you caught that, but this is my intent. Oh. Sorry to snatch that from you.
Is this the file?
There's 3 files. Pick one. R vector. Well, it's going from here to here, from my differential to my point in question, so I'm going to the left x. And I'm going in the j hat direction, the distance r, so plus r j hat. And this is why I like using the r vector instead of r hat, is the fact that it's just so clean right there. I'm not dividing by anything at this point. I know I have to divide, get the r cubed down here, but to me, I'm dealing with one fewer fraction. So B, my magnetic field, is mu naught over 4 pi times the integral. Current's constant, so bring current out. And I'm left with ds, so negative dx I hat, cross r, which is negative x I hat, plus r j hat, over r cubed. And r is x squared plus big R squared. Square root of that, so that'd be 2 to the 3 halves. And just a very quick catch up, Trevor, there are basically 4 variations of this same formula. This is just one of them. This is known as the Biosavar Law. And so we're just doing, this is the first application of it. Okay. So mu sub naught is the permeability, this is a constant. I is current, ds is this unit vector in the direction of the current flow. It's just some physical distance in that direction. R is from my differential to the point where I'm trying to find the magnetic field. And so that's R vector with the length of R. So that's the quick and dirty. It is on videotape, so you can get to the very beginning. All right, so we have a cross product here. And I did do the unfortunate thing of using X, because recognize this is an X for cross product, and this is an X because of the variable X along the X axis. So these 2 X's are not the same.
Can you read that bottom piece again?
This down here,
Yeah.
X squared plus R squared to the 3 halves. Is that all you needed, or you need?
Yeah, that's fine.
Okay. Pythagorean theorem. I know you didn't ask for this, but R squared plus X squared. I'll tell you what I'm gonna do. This X for cross product, I'm gonna make a different color. There we go. Now the X's are different. Unless you're colorblind, then you just have to trust that they're different colors. All right, flashback to how do you do cross products. What is I cross I?
0.
What's I cross J?
K hat.
All right, so I end up with mu naught I over 4 pi. Integral of, let's see, I cross I is nothing, I cross J is K, so I get negative big R dx K hat. The negative R dx comes from, well, there's my negative dx and there's R. and then I cross j is k, over x squared plus r squared to the 3 halves. Gonna do one more, pulling the constants out. So I get negative big R mu naught I k hat over 4 pi. And then an integral that we have seen before. We do have it all in a single variable, so we can do limits of integration. What are my limits of integration?
Negative infinity to infinity.
That is the intent. I don't remember if I mentioned that's an infinitely long wire, but it is. So if I did not, thank you for reading my mind. If it were finite in length, then obviously you'd put down some finite number. Bring it up here. Negative R mu sub naught I k hat over 4 pi times. What is this integral?
In the formula sheet.
All right, so we'll go to the formula sheet here. That one right there. So it is x over r squared square root of r squared plus x squared from negative infinity to infinity. This r up here cancels out with one of those. So I get negative r u naught I, oops, that r is going to go away, k hat over 4 pi r times. So I brought this r squared out. You plug in infinity, you get 1. You plug in negative infinity, you get negative 1. 1 minus negative 1. So now I'm left with negative mu sub naught I k hat over 2 pi r. Magnetic field from infinitely long wire. To a point at distance r away. There are a couple things to pull from this. Number one, the direction at point P of the magnetic field. Recognize that the direction is established by this right here. Those are my vectors on the right-hand side. That cross product should be in the same direction as my magnetic field. ds is the direction of current. R hat is the direction from that point to up here. I only care about the perpendicular components. So in essence, ds cross with the perpendicular component to my point going into the page. Typically, the way that you would do this is you would treat it like a hitchhiker. The current's flowing to the left. I point my thumb in the direction of the left. On top of the wire, my finger's going into the board. So my magnetic field is going into the board on top. Down below, my fingers curl out. So my magnetic field is coming out of the board below the wire. So I would expect my magnetic field to be going into the board up on top, out of the board on the bottom. So my magnetic field from that current is flowing around like this. It's one of many right-hand rules that show up. So. The other bit. Where have you seen that before?
Circle. Circle.
More specifically,
Cylinder,
pardon?
is it a cylinder?
Still going, what does this have to do with a circle or a cylinder?
Circumference?
Yeah, that's the word I'm looking for.
Circumference, yeah.
We'll use this. So if I have a current running down the axle right here, my magnetic field, so if the current's flowing that way, then my magnetic field is flowing around this way. That's my magnetic field's going around like that. There's no reason to think that the magnetic field here would have a different magnitude than here, or here, or here. The magnitude of the magnetic field, the same distance away from this line, this imminent line of current, should be the same. So, if I multiply both sides by this 2 pi r, there we go, I get negative mu sub naught I, k hat, is equal to b times 2 pi r. This is a pseudo derivation. I'm going to do a little hand waving here. This is just the circumference. The negative k hat comes from, well, actually, let me do a dot product with negative k hat on both sides. So on the left-hand side, I get mu naught I. This is still a pseudo derivation. And on the right-hand side, if I just do b dot L, and just make sure that when I'm doing this line integral right here, or this line, not quite the integral yet, when I'm doing this line right here, I go in the direction that the magnetic field is traveling. We can generalize it one step more, and that the integral of b dot dl, now it's an line integral, is equal to mu naught times I. This I is the enclosed in the circle. This is known as Ampere's law. I think the accent goes there. Ampere. Who's got a good French accent? Then you are stuck with mine. I think it's Ampere's law. But it's gone through Ellis Island and Ampere. So you have a line of current, 2 amps right there, traveling up. At this point right here, in which direction is the magnetic field going?
On the left side, it's out of the board, and the right side into the board.
Okay, yep. So over here at that specific point, it would be indeed into the board. Over here, it's going to be out of the board. And again, it is the right hand rule, it is not the dominant hand rule. If you are left-handed, it is still a right hand rule. I probably asked this before. Any left-handed people in here? Okay. Way to be different. Yeah, I saw you pull up your right hand when you were doing it just then, so I don't think there's going to be an issue. Now, case number 2. I have a loop of wire here with a current flowing counterclockwise. I want to know what's the magnetic field smack dab in the middle. We're going to use Biosavar, or Biosavar. We're not going to use Ampere's law quite yet. We're going to combine what we're doing here with Ampere's law in just a moment. Since my current's flowing counterclockwise, then I'm going to create my ds. My R vector is pointing from that to the center. So if I think about at that moment right there, I have ds going this way, I have r going that way. I know I'm gonna have ds cross r as part of the Biosavar, so what is the direction of my magnetic field at the center because of that little segment?
Can you repeat the question?
What is the direction of the magnetic field in the middle of this loop because of that little bit of wire, or that little bit of current? And to narrow it down, it's either into the board or out of the board.
Be out.
We got one vote for out,
What about in?
you voting in, another in,
I vote out.
another out.
Out.
Looks like it's 3-2 at the moment. And some people afraid to be wrong.
In.
I like the boldness.
Out.
It's 4-3 now. We have an odd number of people, we could, I mean, the majority could be right. Maybe I just didn't hear the two voices, they already spoken. When you're doing a cross product, so from this point of view, when you're doing a cross product, you put your hand in the direction of the first part, because remember it's ds cross r. You bend your fingers so that they bend towards the second vector, and your thumb points in the direction of the cross product. It would be out. Looking at it slightly different way, looking at my thumb points in the direction of the current flow, which means that the magnetic field here should be into the board here, out of the board here. If I'm down here, my current's flowing this way. Thumb points in the direction of the current flow. It's pointing out of the board here, into the board here. Matter of fact, over here. Out of the board, into the board. So when I have a loop of wire, I've got this, I could do right-hand rule at any point right there, and my fingers, the tips of my fingers are pointing out everywhere around there with a counterclockwise flowing current. Or a variation of that, because of course, you can't have too many variations of the exact same rule. With a loop of wire, just curl your fingers in the direction of the current flow and your thumb points in the direction of the magnetic field in the middle. So current's flowing counterclockwise, magnetic field's coming out. Current's flowing clockwise, current pointing in.